Well, welcome to my talk, ZFS Performance Analysis and Tools. And in the previous panel, people talked about different analysis tools for ZFS, which is really interesting for me. I picked up a few tools that I now need to go and do some research on and see if there's any extra observability that I've been missing out. In this talk, I'll be talking about the sort of things that I use at Joyent and that we use to solve ZFS issues. And so we'll quickly go through many tools and the sort of problems that they solve. And this may create homework for you as well, for things for you to go and try out. I'm Brendan. These days I do systems performance analysis of the cloud. With ZFS, I've done performance analysis for over 5 years, both for enterprise and cloud storage. I've written many DTrace-based ZFS performance analysis tools, including a bunch in the DTrace book. And while at Sun, I got to do the coding work to develop the ZFS L2R. So I'm familiar with parts of ZFS. At Joyent, we are a cloud computing provider. And I think in an earlier session today, Bill Pievsky went through what Joyent does and why we use ZFS. We're using ZFS for host and guest storage for the cloud. And we use it because it's reliable, it has great features, performance, and it can boil the oceans. Does anyone remember that? When was the last time you heard that said? So ZFS can boil the oceans. If you remember back when ZFS was launched, this is one of the key features. It was effective, it got us all to remember ZFS. So I was reminded of that last night at the Sun party and felt like I should bring it up. ZFS can boil the oceans. Here we build tools for ZFS automation and observability at Joyent, and performance is a key company feature. It's on our website. So when we have performance issues that are suspected to be in the file system, we need to solve them fast. So observability tools matter for us a lot. And also especially that we have people coming from cloud environments that are using other file system types, where multi-tenancy and performance isolation and noisy neighbors are common issues with disk I/O and with file system performance. And so people come in expecting to see more of this type of issue. And so for me at Joyent in particular, being able to prove very quickly that now that you're on ZFS and now that we can show you what's going on with DTrace, we can show you that it's not noisy neighbors, it's actually something else, or maybe it is noisy neighbors, although we did do ZFS I throttling. So it's very important for us. The agenda, I'm going to go through 12 tools for ZFS performance analysis. These aren't particularly sorted. And I've got a couple of extra ones to mention. For cloud computing from within a zone, and I talked about these a little bit briefly yesterday at Illumos Day, a couple of extra ones that I get customers to run. So starting with Unix 101, a functional diagram, what the full stack looks like. We have logical I/O at the top. That's what the process is doing to the file systems via the virtual file system layer. Way at the bottom, you've got physical I/O going to the disks. And when you're using IOStat is often asynchronous. The I/O that you're looking at is often asynchronous with regard to the process. That's because of, say, write buffering, where we're writing to DRAM for default writes, and also for read ahead. In ZFS, that's prefetch. And there's also various other I/O types that originate from ZFS itself. So things like resilvering will cause a lot of I/O, but there's no application doing that. The ZFS is doing that itself. So using IOStat to figure out what performance looks like way up in the application is kind of tricky. For the application, I'd really like to look between the process and VFS. That's in synchronous context. And that allows me to see the latency induced for the application when it blocks doing file system I/O. And if I measure it way up there, then I'm capturing everything. So I'm capturing, there could be ZFS locking issues as well. And if you're using IOStat, you will not see them. With IOStat, you're just looking at disk issues, and it's not quite in the right context. But by going way up to the process, we can confirm things much more quickly and immediately tell the customer, yes, it is the disks to blame via ZFS, or most of the time it's not, so that they can then focus their efforts on where things really are. In this quick talk, I'm going to go through, like I said, 12 tools, and it gives you observability all over the place. So, and that's the point. We want full observability to find out how I/O is being processed across the map. And so from the top, at the user level, my for example, MySQL pip fslatency.d to look inside how the application is experiencing file system latency. Then going down to the syscall interface we can do. In VFS, the VFS to ZFS interface, I use that one a lot. Inside ZFS, then the block device interface, and you can go down into the lower disk I/O subsection. I've got a bunch of scripts in the DTrace book that does that, and that's things like looking at how the SATA driver works and SAS drivers, MPT, and so on. That's just my top 12. Many of them are DTrace-based, not all of them, and you can create more as needed. And it's kind of really exciting. I like, this is a functional diagram of ZFS, and for me, for a performance guy, this is exactly what I want, because I get to DTrace everything, and I get to really narrow down exactly where the latency is. And so I love these diagrams, and there's more detail inside ZFS for us to examine, and I get to DTrace all the things as a day job. And in the Joyent cloud, when I have all sorts of different applications running on top of ZFS, I get to see ZFS pushed in exciting different ways, so I get to write a lot of cool scripts. But I'll start with something that's not new at all. This is really old, IOStat, and originated, I believe, from the 80s, from AT&T Unix. And as a performance tool, I actually do like it. It is fairly well designed. It's giving us the ZFS to disk workload on the left. So those columns, reads, writes, kilobytes reads and kilobytes written, and then disk resulting performance on the right. It may look a little bit different if you're on Linux or you're on FreeBSD, but it's basically the same information, and the same role. This is tracing at the block device level. IOStat is an effective tool for a particular class of issues, like when you have disks that just go out to lunch because there's maybe a perk ECC error, or there's some sort of controller error, or the disks themselves, they've received I/O but they're not completing it, and they should be soft erroring, or they should be hard erroring, and they're not. And it's terrible for ZFS, because ZFS can't fault the disk. So this is something that does make me cry as a performance guy. You see performance drop off, and the disks are basically dead. They should have died. They should have told the operating system, I'm dead. I'm doing I/O at 5,000 milliseconds. This isn't really doing I/O. This is me basically being dead, or very close to dead. Not dead yet. That's the problem. Definitely dead. So please, disks, please tell me that you're dead when you get beyond 1,000 milliseconds. This is something that we have struggled a little bit with in ZFS.
They're persistent.
What's that?
They're persistent.
They're persistent. The disks themselves, they want to keep going on. It's like, not dead yet. Here's 5-second I/O latency. How about 6-second I/O latency? No, how about you just tell me that you're dead? Give me a hard error, and ZFS will go and use a different device. So, IOStat is good for that type of issue. You can see, I mean, this is actually from one of those issues. In the percent busy column, I've got 100%, and there's no I/O. You're dead. Tell me that you're dead. So there are some minor nits with IOStat. It does not show read-write latency separately, and so with ZFS, the transaction group flushes drag up the latency, which looks alarming to customers, but it's asynchronous. You can use DTrace to split it out. I think most operating system kernels, they do track the latency separately. They use the Riemann sums within the kernel, and it's conceivable you could just add the column to IOStat so that you can see this, separate out the latency. I generally just reach for DTrace when I need to do that. There's no higher level context either, so PID, ZFS dataset, file path name, it's fine because that's not really the role of IOStat. But we often need that to really understand performance issues, to express it in the context we need. There is a major problem, although this is not IOStat's fault. IOStat is commonly confused with application level or logical I/O. So the I/O rate sizes and latency can dramatically differ between the logical file system I/O and physical disk I/O. They can differ by orders of magnitude. And one obvious reason is you have a very high cache hit rate. So in the Joyent public cloud, we have systems where the cache hit rate is, we had some very large customers where it was 99.97%. And so the amount of logical I/O you're doing to ZFS is pretty high, and it's returning out of the ZFS arc, but the actual physical I/O is very low. And you really need to understand that difference. That's why I had that Unix 101 diagram, so that you can understand which level you're looking at. And if you are looking at IOStat and you're kind of getting confused by it, you can be drawing the wrong conclusions. And as a performance guy, I get this a lot with customers where they're kind of confused about what's going on. And they're doing it because they're using IOStat data, or they're using some sort of GUI that's based on IOStat data. So there's a lot out there. This one I've picked on. This is the Moon and graphs, although there are many. And when you use these GUIs to start with, you think, wow, this performance observability is fantastic. There are so many graphs. Everything must be in there somewhere. I just need to find the right graph. And it looks really pretty, and it feels like you're really getting to know the system. But a lot of these are based on IOStat. And so when you see so many graphs, I see so little visibility. You're just showing me that thing. I want to know everything else. So going up the stack, going up to the VFS level, one thing we did at Joyent, or Bill Pievsky did, was write a VFS stat command. This is based on IOStat. And now we're looking at the app to ZFS workload. This is logical I/O, and then the ZFS resulting performance. This is a companion tool to IOStat. So VFS stat is up at the VFS layer, IOStat is down at the disks layer. And in fact, there's a couple of columns there for ZFS I/O throttling, because we're a cloud provider. That matters a lot for performance isolation. So fantastic tool. Like I really need this. This one has the breakdown by zone currently, but it's possible that we could add breakdowns by other dimensions. Although there comes a point when if your tool gets too sophisticated or too niche, you can leave that for DTrace scripts. Where it's like, well, you can just write a DTrace script when you need that particular piece of observability. This thing is so common, it is a good idea to have it built in. This is built into kstats, and so the kernel is maintaining those counters. It's a good high-level summary of logical I/O and summarizes by zone. The impetus was noisy neighbors on the cloud, and so they can see the actual latency that they're suffering and not getting confused by IOStat, which is confusing. And it summarizes the performance that applications actually experience. The next script, ZFS slower.d. This is one that I tend to use a lot. It shows ZFS reads and writes. I'm tracing at the VFS to ZFS interface and printing out various details. If you give it no arguments, it traces everything, which is a bad idea often because it's thousands of pages long per second. If you give it an argument, it will filter based on that milliseconds. So here I've said, only show me the ZFS I/O slower than 10 milliseconds. This is really cool, and I use this tool almost every day. When customers say, I think they're slow disks, and I think my slow queries outliers due to the file system returning slowly, I can go and immediately trace them. I'm logged into the cloud here. I'm just typing one-handed. I'm running a version of ZFS slower dash trunk, and I want to make sure that I got this right and I don't run the wrong thing. Yes, there's my truncation. This is ZFS slower dash trunk because I'm trunking off the file name because it's confidential. I can't just demonstrate. Here's some customer file names, but I can give you the high level because that's sanitized, and I can run it with 10 milliseconds, and it tells me that I need to pfexec it. Now this is what Ben Rockwood talked about yesterday when he talked about setting up illumos for the Joyent public cloud, and he said Brendan has permission to run DTrace scripts on the cloud. This is what he's talking about. This pfexec goes into role-based access control. Again, now I'm allowed to run this. Good. So this is, please be truncated. Yes, good. Whew. No, I'm not accidentally showing you custom things. This is showing us the ZFS I/O for this system that's slower than 10 milliseconds. And if I was interested, and you can see there's some of it. I can dial up 100 milliseconds and probably wait a while. I can dial up 1 millisecond or whatever I want, arbitrary. This is probably going to be too noisy. I think this system is running with a very high arc cache hit rate because I know it is actually fairly busy. It's doing more disk on. So I'll leave 100 running and we'll see what we catch. This might be embarrassing for Joyent, but it'll show you the power of the observability. So ZFS slower, I use that all the time. It's great at identifying outliers, and of course I can enhance the script and include application level context to express the latency in application context like the MySQL query string if need be. So I had examples in the slides of, say, 100 milliseconds, it's less frequent, or all reads and writes. It's written using DTrace. It was stupidly easy to do because there is a really nice interface between VFS and ZFS, and I'm sure a lot of you who have worked on the ZFS implementations know this. Sun has a nice, clean way of mapping those interfaces together, which gives me nice, neat functions that I can go on DTrace, and they're synchronous, and I can just time entry to return. And that's on GitHub. It's part of a suite of tools I've got under my GitHub account. Oh, that was actually the map, so those are the functions I'm tracing. IOSnoop is another popular tool I've written, although IOSnoop is working at the disk device level. If you have MacBooks, and I can see quite a lot of MacBooks, you can run sudo IOSnoop, and it's been shipped for a while in Mac OS X. They shipped a bunch of my DTrace-based tools. And it's tracing the block device level, so I can see the actual disk I/O performed. Here, beam.smp, this is actually a React database, and it's showing me various details. You can give it some options. DOTS is giving me start time, end time, deltas, and other variations of delta times, disk time, and so on. I actually use this if I need to log something and then pick through it I/O by I/O. And then post-sort the start or end time columns, because as Adam has told us yesterday at Illumos Day, DTrace for a very long time has not had the ability to print out in the correct time order. It just prints things out a little bit shuffled based on the CPU buffering. And now Adam and Matt have added a way that you can post-sort the output. So anyway, I do have these columns as due in part to post-sorting, but they're also useful in terms of debugging. Sometimes disk I/O issues you can understand by reading the order and sequence of the I/O. If, for example, you have reads queuing behind writes, and so getting all the detail can be important. It's written using DTrace. It's from the DTrace toolkit. That's actually using an I/O done probe. I shouldn't really have Genunix in there. I should drop that. Although then it matches NFS. Although it's yeah. I can improve that a bit. It's from the DTrace toolkit. In fact, that version I had there was a newer version I haven't released yet, where I put the units on the columns. I've put microseconds. It's 370 lines of code, and that's mostly getops to process options. And that's because DTrace doesn't have the getops function, and I'm looking at Adam in the back. Although it doesn't matter, DTrace doesn't need to do that. You'll see there are a lot of the DTrace toolkit scripts that wrap DTrace in the shell, which is a reasonable use of a reasonable way to use DTrace, so that you can offload that capability into the shell, which already does it. So it's actually mostly just a shell wrapper. I wrote it in 2004 to solve disk I/O by process, and it's now, as I said, it's shipped. It's also in Oracle Solaris 11, although I haven't seen it there myself yet. I wrote a companion tool called IOTop, and a similar IOTop later appeared for Linux via the block tracing framework. So it's great to see that idea is useful and benefiting the Linux crowd, although I'd prefer they did it via the original DTrace framework. It doesn't do ZFS path names, and you saw from the output earlier, it was, since I'm at the block device level, the path name column on the right is none, and it's because this worked at all was kind of a party trick. It was the way we cached the vnode path, and the vnode was still valid by the time we got down to the block device layer. And ZFS aggregates I/O, so we don't have a pointer to the vnode, and we can't easily do this. But there may be a workaround. We've toyed around with ideas to work around this. And if you're at the Illumos hackathon tomorrow, you can have a swing at fixing this and have the path name column show something meaningful so that we can use IOSnoop again on ZFS. That'd be cool. So IOSnoop, another good use for it is to locate the origin of latency. So here I've got ZFS slower and IOSnoop, and by running them both side by side, if I have big latency in ZFS slower, and then pretty much the same big latency in IOSnoop, the problem is the disks. If I have big latency in ZFS slower, but just nothing at the disk level, anywhere close, the problem is probably inside ZFS. And then there's a middle ground, where you have a big ZFS I/O, and you have a bunch of small disk I/O that kind of added together, because ZFS was doing some metadata stuff. But it is very useful to correlate them together to figure out, to try and locate at least which area the latency is originating from. Another tool I wanted to mention, although it's not really a tool, it's just a one-liner, iostacks.d. And I guess you could make it a tool. It would just be a one-line tool, a one-line script. I do use this quite a lot, and it's detracing the IO start probe for block device IO and showing the stack backtrace. This is fantastic for understanding why did the kernel ask the disk to do some IO. And so this gives you the ancestry, and I can read through this and figure out, oh, this one's a ZFS read coming from the syscall layer. It looks like it's an arc miss because we went from arc into ZIO and so on. In fact, you could, because normally it will print out a bunch of these, you could have a stack recognition chart. So here's a syscall read arc miss, and I've got a ZIO pipeline. It's originating from the task queue. Another good location to trace, apart from IO start, is ZIO create, because with the way ZFS does pipelining, another thread may pick up an IO by the time it actually issues it to disk. And so if you're looking at the stack trace, you're only seeing that thread's stack. And so it can be handy to try and wind up a bit and go to the point where we created the ZIO to enter it into the head of the pipeline. I wrote this slide like 1 hour ago. I don't know if there's actually a better way to do this. I need to spend a bit of time reading the ZIO code. But the notion is you're looking at when IO first entered the pipeline, it didn't have a parent ZIO, so you can see the stack for when that was created. And so I have solved problems using this before. But anyway, there's probably about a few dozen of these stacks that you'll see from time to time, and they really explain what ZFS is doing. You could almost have a stack recognition chart of stack traces for ZFS. It might be the world's most boring set of playing cards, but it'd be very handy. This will identify some unexplained additional I/O that originates from ZFS. Things like resilvering, you can see it out of there. I'm talking about the ZIO. Metaslab free, another example tool. We did this at Joyent, and I've seen something similar before. I think Rob Bourbonnais had done this before when I worked with him at Oracle and so on. So Metaslab free with ZFS, it breaks up the disks into metaslabs. They can be 10 gigabytes each or variable. They're a little bit like, as far as I understand, they're a little bit like cylinder groups from FFS. And they have a different algorithm as they fill up. And they start off in the first fit, which is nice and fast, and then they go to best fit, which is not that fast. And for customers looking at their performance, you would look like something like a picket fence, and it would have like a square wave as they go from best fit to fast fit, down to best fit, back to fast fit. As you filled up each metaslab, then it went to a new metaslab and started filling from there. And so the idea was we wrote this tool, I can probably just run it. Oh, I got some 100 millisecond plus I/O. Whew, not too bad. But 194 milliseconds? Are we using the slowest disks ever?
No.
No? Yeah, the voice of pain. Yeah, I mean, you will sometimes get high I/O because it's the tail of the queue and it's queued behind other I/O that were issued. But yeah, I've seen a lot longer than 194 milliseconds. I just want to run the metaslab so that we can see. I was just running this earlier. We can see this is a machine on the cloud, and it has a React database on it. And it began by telling me the tunable right now is 4%. That was right at the start. And that's tunable, and that's something that we've lowered so that the metaslabs spend more time in first fit. And on the left, it says we're currently writing to 2 metaslabs occasionally. One is at 99% full, 99% free, and the other one is 26% free. And on the right is the number of allocations to each. So currently ZFS is running to 2 metaslabs, and since they're above the tunable, it should be using the fast fit algorithm, so expect high performance. If this dips below the tunable, and we notice the big drop in performance, that would allow us to correlate and understand why. So that's kind of why we wrote that tool. It's written in DTrace. That's the entire script. It's actually pretty short. FPT metaslab dfalloc, so it's using a kernel dynamic tracing, and then tick 1 second, every second we print out the information. And I put it on GitHub. And I talked about what that is for. And we use it for tuning so that we can understand if the tunable is in play. Sometimes when you're, let's say you set the tunable and then performance is better. What's actually happened is, coincidentally, ZFS is now using a new free metaslab. It's like, it wasn't the tunable, it was because you just timed it badly. So I do run this script as part of tuning. SparSync.d is another go-to tool. This traces the ZFS spar syncs and use it to check for correlations with IO latency. If there are latency bubbles at the application level that correspond here, then we know why. And of course, the ZFS spar is tunable. We can change the rate at which it syncs out so that they're smaller and interfere less. It's not such a bad script. That's pretty much all of it. I put that on GitHub. So it's tracing disk.io and then the sparse sync routine and timing it. It actually has a very long heritage for a DTrace script. I think Matt wrote the first one, and then Rob Bobbinet was improving it or adding things. Ben had it on his blog. Now I've been playing with it because I've got it into the DTrace book. So a lot of us have worked on it. Just a useful tool that we use to look at that type of latency origin and for tuning. Another really useful tool is %IO weight. And you can see %IO weight as the column in MPStat. I'm just trolling. Like, I'm seeing if anyone's awake. No, this is still 0. %IO weight, we actually hardwired this to 0. This is not part of my performance tools. Sorry. It's still 0. We actually go and use DTrace and everything else if we want to find out what's really happening. %IO weight, if you're curious, and I don't want to get on a tangent, but it was very confusing to interpret and in some ways irresponsible for us to allow customers to continually be confused by this because we'd seen this so much. And so it was hardwired to 0 in the kernel for this last 10 release. And so now people say, why is IO weight 0? Because we're trying to be responsible and we know that this confuses 9 out of 10 customers and we're trying not to lead you down that road. ArcStat, back to the real tools. ArcStat is for ZFS Arc and L2 Arc statistics, and it is written in Perl, uses kstats. This is not a DTrace script. In FreeBSD, it was ported and uses sysctl. Statistics are per interval. We can see things like reads, Arc, although most of you probably know Arc is, of course, the primary cache for ZFS, the adaptive replacement cache. And so looking at details like cache hit rates, cache miss rates, the volume of traffic, the size of the cache, how that varies over time. These are important primary metrics for understanding performance. Written in Perl, uses kstats. That's ZFS colon arcstats. You can see there's a version on github.com/mycache, arcstat. And originally by Neil at Sun, and then Jason Lenthal from FreeBSD has done a port. And it's crucial for understanding cache performance. And it does, the latest version has switches for the L2 arc. I'm still in the habit of typing kstat minus p and arcstats, which is harder to read. I need to get out of that habit. In fact, if I look at this on my system, so I just checked that it worked. There we go. We have a 0% miss rate, which isn't too surprising since this system is running, it's wrapped. The arc size is 80 gigabytes right now. So one of the benefits of the way we do cloud virtualization is that when you're in zones, you get to share the arc. And so you have customers who can have these phenomenal hit rates because they're able to use much more than their allocation. And so very high hit rates on Joyent is not unusual. Arc access to D just is another example of a tool. This one's going into the ZFS Arc using DTrace. This one looks at the Arc population age, and right at the top, it's printing out the age, and we've got 10 milliseconds. It's printing out the age in terms of LBolt. So LBolt is on the left, and then I've translated it onto the right to something human readable. And of course, LBolt is variable, so it might actually vary. So right at the top, we have most of the Arc accesses for buffers that were accessed within 10 milliseconds. So really frequent data. Then you have 1 second, 1 minute, 1 hour, and 1 day. This is a consequence of Joyent's huge amounts of the Arc that we use, is that for some customers, it means there is a buffer in the arc for an entire day between accesses. So that is a dinosaur of a buffer that has lived in there. And so obviously that's why people get such high cache hit rates, because it takes forever for it to finally be evicted and pushed out. That guy was written using DTrace. It just goes and I have to read this from time to time because I'm surprised that I even wrote this, because getting having any sort of visibility into what the arc has inside it is really, really cool, and also really, really difficult. So the arc buffers don't have a lot of metadata because there's so many of them, and that would be expensive. And so I am very delighted I was able to get something out of here. And I've got a whole blog post about activity of the ZFS arc using DTrace scripts. That script actually helps determine the working set size and the turnover rate. Because for the working set size, it's a really important question if you're sizing systems. How much DRAM do I need? How much cache do I need? It's actually a really hard question to answer. This gives me an idea, because if let's say I want to say working set size is data accessed within an hour, I get to have some sort of age information from within the arc to help answer that. Like at the moment, the arc is sized so that I can definitely cache the working set size, because it's got things in there that were a day between access. Another quick tool, kstat-p, zone, VFS, ops. These were counters that Bill Pievsky from Joyent added. These are pretty simple but pretty useful. What they do is they just increment when I/O has been slower than that millisecond range. This is hugely useful for doing post-mortem debugging of an issue. Well, not post-mortem, but post-debugging of an issue. The customer said, we think we had a really bad disk event, and can you take a look? And so I can look at these counters and say, well, at the VFS level where it matters, did you actually bump any of these watermarks? This particular system has had, we've actually had, whatever that is, 64 million 10 millisecond and slower ops at the VFS level, and 173,000 100 millisecond ops, and 431 second ops. Whew. Thank goodness we didn't get to the 10-second range. There's a reason why we added that counter. I hope I don't get to the point where I'm adding a 100-second counter or asking Bill to. That would be very sad. I have 10 seconds, surely that's the end of it. That's the longest counter we'll need to add. But it's hugely useful to get that information. And based on the other counters, this looks kind of bad. It's not that bad. It's actually 0.00002% of the workload based on how many reads and writes that file system actually did. So this is a system that's been up for a long time and has been very, very busy. And so maybe a few I/O queued behind some weirdness out of the Dell perks, or a sparse sync or something like that, and reached 1 second, but a very, very small fraction. Scatter plots, I do tend to use these as a tool. This is starting to get to the last resort tool if I'm trying to understand some disk issues, especially disk controllers and lower, where I will run IOSnoop with the timestamps to a file, use a bit of awk or Perl, GNU-plot or R, and then I get to see what's going on. I use scatter plots to determine that for our systems, based on the perk cache flush interval, we were having quite a lot of reads were queuing behind writes. And I can see you see these groups of writes, and then a spike in latency of reads would happen shortly afterwards. And those guys are getting queued. As far as we know, we'd much prefer not to be using storage controllers and to let ZFS manage it, because then we can see the disks directly. So, yes. That's what I want, because I can't detrace the storage controller. I want to detrace everything. I want to detrace all the things. But I need to get rid of the storage controller so I can actually look at the queues and see what's going on. So scatterplots, great, last resort. Heat maps are what we're using at Joyent, and other companies are starting to use them too. They're really fun. This is a latency heat map at the file system level. And on the y-axis we have latency, file system latency. On the x-axis is the passage of time. Each I/O is quantized into a bucket. The darker it is, the more I/O fill into that bucket. Heat maps especially are necessary in the cloud because you're doing so many thousands of I/O. You can't do a scatter plot. You can't do one of these because you're talking about the system may be doing 100,000 VFS level I/O, and now multiply that by 1,000 systems. And so now you have 100 million just points, scatter plot points. And it would look like paint. And you also have a lot of those XY coordinates to move around the cloud and try and render in real time. So it actually does become, scatterplots are great because they help to identify patterns that, sorry, the heat maps are great. They help identify patterns that scatterplots can't do, because scatterplots have that resolution limit. So the y-axis, the higher it is, the slower that particular I/O was. And we get to visualize all the individual I/O. This is the VFS layer. And this particular example I've got was a benchmark I was doing where on the left you can see there's this cloud of disk I/O, and then there's this gap, and then there's the line at the bottom. The line at the bottom is the DRAM hits. The cloud, the scale, by the way, is 30 milliseconds. The cloud is disk I/O latency, so rotational disk latency. Anyone guess what those 5-second spikes in latency are? TXG flash, yes. So you get used to looking at that pattern. Your eyeballs get to recognize it. And of course, if that starts to become a problem, you can tune it and modify it, make it go faster. And we definitely use heat maps to tune it there. At the point in the middle of the graph, that actually became cached, and that cloud of disk I/O vanished, and then we're just hitting out of the ZFS arc. Bimodal distribution. And this is one of the reasons I don't like line graphs very much. Line graphs serve some roles, but there are many roles I need to see the full distribution. Imagine taking the information on the left and then presenting it as an average latency as a single line. That doesn't make sense. Imagine expressing the standard deviation for the data on the left. It doesn't make sense. Because it's not a normal distribution or a Gaussian distribution. So when people are showing me these average latency line graphs, and it's like, hey, it's really cool, it does average latency and standard deviation and 99th percentile. It's like, are you sure it's cool? Because you're assuming it has a normal distribution. You're not sure. It may not, it may be bimodal. Bimodal distributions happen a lot because you have the cache hits and misses, or you have the fast code path and the slow code path. And so this is one of the reasons we're using heat maps. We're not using heat maps for everything. It is a tool for the job. It just happens to be a tool for many jobs. We will use line graphs as appropriate as well. And a last heat map example. This one shows how bad things can get. The y-axis scale this time goes up to 5 seconds. This is looking at latency outliers cloud-wide for an entire data center. And we've got good latency, bad latency, which is like tens of milliseconds, very bad in the hundreds of milliseconds, and then inconceivably bad latency in the 4 to 5 second range. Like, this shouldn't happen. When you have that resolution, and you can see the outliers as spots in the heat map, you can see what's actually been there all along. If you were looking at the average latency from IOStat or any of the derived GUIs, that could be averaged away. You may not know they're occurring. So within a zone for cloud computing, suspected noisy neighbors were hurting ZFS performance, and ZFS I/O throttling was added to address this. We needed the ZFS observability to confirm deny issues from within a zone. So the previous tools I just showed you, a lot of them were, you need to be operator on the box or global zone access to run them. So I run them a lot. But for this slide, I wanted to mention there are a couple of things you can do from within the zone to understand ZFS latency. And that includes tracing, for example, using the DTrace PID provider for MySQL PID latency. And I went through that in my talk yesterday. Or syscall tracing when you are doing ZFS-based I/O. And so I've got a couple of links there. And so it's really helpful for us as a cloud provider to also give scripts to customers. Customers can log in. So these heat maps are for both the operator and the customers, so they can see it themselves. But there's also ways they can write scripts and then trace I/O manually as well. So to recap, we have the observability everywhere, which is great because it helps you narrow down the source of issues. And there are more tools. It's kind of painful to stop at that many because there are more. And like Richard Elling has a bunch of DTrace scripts on his GitHub page for ZFS, and a lot of the other engineers have written some cool things. ZPL IOStat, ZPL status, of course. Like, is the pool degraded? Is that why you have bad performance? Is it resilvering right now? Is that why you have bad performance? ZFS get all. a methodology I believe is called static performance tuning, where you're just looking at the configuration of something because that may explain why it's performing badly. So things like does the record size match the workload? Is compression turned on? Is dedo turned on? So the sort of things we want to check. And ZIO stat is something recently added by Jerry. And you can write much more tools using DTrace to the point where it feels like you're doing nothing but writing tools, but you're also solving issues. There are so many things. This is when I remember that there are so many things I haven't detraced yet, because there's so much stuff you can detrace. I have to detrace all the things? Yes, I have to detrace all the things. An example of detracing all the things, or just about, from the DTrace book, that's just showing a list of the scripts from the disk.io chapter, which is for the disk.io subsystem, a bunch of scripts for the block device layer, for SCSI, for SATA, for IDE, and for SATs. And of course, these are nice short scripts you can take and customize as you need. And then chapter 5 has a whole heap more scripts for file system level tracing. In the future, more tools as needed, especially as we're working on customer issues. So need to be careful not to just create tools for the sake of creating tools. These need to lead to tunables or actionable items. Because too many becomes unwieldy, like the sort of Swiss Army knives that have too many things and you hurt your fingers on, and you just want something simpler that will actually do the job. Thank you. Any questions on tools? Do we have enough time?
Very little.
Very little time, okay. Any questions on ZFS performance tools? The slides, I put them on SlideShare, so.
And we do have some copies of the book that need homes.
We do have some copies of the book. What was the first question? You get a copy of the book, sir. Ask Deirdre. Go ahead.
So I was wondering, what percentage of the DTrace scripts that are out there right now work well on Solaris 10 versus Illumos? Can you give us an idea of how much work has gone into Illumos and what we'd be missing out on?
So the question is, which DTrace scripts work well on Solaris 10 versus Illumos versus Oracle Solaris 11? Maybe it depends on what they're tracing. At the FBT level, kernel internals, things change, and so a lot of them won't work. But they won't work for very small changes. You just need to tweak them so that they match the changes in the code. Which also means you kind of need access to the kernel code so that you can do this exercise. Otherwise, good luck using FBT. That's something that the penny hasn't dropped for a lot of people yet, but DTrace without the kernel source code is really hard because you're in the dark. Now, the hard thing about, not to get too much on that tangent, the hard thing about DTrace scripts is just coming up with them. Like, sparsync is a great idea, and like even if it was broken, I just fix it. Doing things like the arc access by LBOT is a cool idea. The Metaslab free so that I can know when to tune. What's more valuable is just the ideas of the scripts so that you can see the sort of problems they solve in the output, and then actually porting them as the kernel changes is not that much effort. So I am aware that many of the scripts will break and need minor changes. You can like email the ZFS lists for help or go through the code, and most of the effort is just thinking, yes, this is a really good thing to trace. Did you have a question up there? Sorry, did I see another hand? Any other questions on ZFS performance tools? Okay, I'll hand the floor back to Deirdre. Thank you.